I think the audio now works. Let's get started. This talk is titled, Where Did Random Go Wrong? And this is kind of a leading question because it assumes that it did go wrong, but I hope to convince you that it did in fact go wrong, very, very, very wrong. So I want to start with two quotes. The first one is by Stephen T. Lavavey. I hope we all know him. And it's, random is really elegantly designed. I love this header. And the second quote is by Andrei Alexandrescu, another very smart C++ person. And he says, I think it's the best random number library design of all by a mile. You know, and that's a lot of very high praise. And then nobody actually uses random in practice. Right? Show of hands, who here uses random in their code? Oh, I see two people outside of tests where you don't care about the inputs. I still see one people. Okay, interesting.
Wow.
So why? Why does nobody use it? So some people say they don't like the complexity. You know, like to create random number, like let's say I want to have 1d6. What I have to do is first I need to get some entropy from somewhere. Then I have to get a random number engine. Then I have to get a random integer distribution. And then I can finally get a number. Let's take a look at what it looks like in the code. You know, okay, so first we get ourselves some entropy source, random device. Then we get an engine and we seed it. Then we get the distribution, and then we finally call this distribution on the random number engine and get our number. You know, like this is kind of complex, kind of annoying, but is it really, this is complex, yes, but is it really a problem? And my answer is no. Look, all of us here, we are programming in C++, you know, like, if we are programming in C++, you have to deal with GL values, PR values, X values, L values, and all of this stuff, and that's just the value categories for your code. Oh, then you have to deal with overall resolution, universal references, and no, like it's fine. Compared to C++, this is easy. But the issue is there is no value in the complexity. What do we get from the fact that using random is complex? Well, but we don't get anything, right? And in the example I showed you, we just took random device, some random bits, and you know, we got some 1d6. Let's say that's not what we want. Let's say, and we want to have it reproducible. Again, code example. Okay, so we say we will take some random number engine as a template by reference. We create our distribution that we want. Then we call it, and you know, this is good. We are done. But the question is, you know, we are using ints. Why are we using ints? When uint8 is just big enough for 1d6, you know, like numbers 1, 2, 3, 4, 5, 6. 1 byte is enough. Why use 4 bytes? So we rewrite the code. It's easy. We just say, okay, actually, uint8, call it, done. Good enough, right? No, this is undefined behavior. Why? Because there is this clause in standard that says, through this subclause of round, the effect of instantiating a template. Please notice we are talking about instantiating a template. Literally having this code anywhere in your binary is UB. You don't have to call it, you don't have to do anything. Instantiating is enough. There's a template type, parameter named, uint type, blah, 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 is undefined unless it's one of unsigned short, unsigned int, unsigned long, unsigned long, long. And that's the round track general requirements. I think it's paragraph 1, subparagraph 6. You know? So if it's not one byte, if it's not one of these 4, it's undefined. What the hell are we looking at even? So, you know, we knew about this in a long time. STL, Stephen T. Lavavey, has opened a library issue 2326 about this more than 10 years ago, okay? So what was the resolution? Note a defect. The library issue was closed as not a defect in 2017, 4 years later. No, this is fine. This is completely fine. So actually, 2 months ago, a new issue about the same thing was opened. It was for 4109. And this time, it might actually progress a bit more because the old issue was unfortunately worded. It was about how it doesn't make sense not to allow this. And this seems like it shouldn't matter, but it does matter a lot. If you have ever done some standardization work, you know wording matters a lot. Catching the right people in the room matters a lot as well. So this issue actually is much more forceful about the fact that it's undefined behavior, which is quite frankly insane. Like if we had actual reason to disallow uint 8t or something, then we can say this is disallowed. And the implementer just will add an aesthetic asset. This is easy. But no, yeah, let's go back to the previous design. You know, we now know that using uint 8 is undefined. So we go back to using an int. It's fine, it works. And of course, it is one issue, right? We did this for reproducibility. It's unportable. You know, like you can't assume that this. Wait, what? Okay, I have a slight issue. For some reason, this doesn't come up the way it should be. Interesting. I will have to figure out what's the issue later, but sorry, there is supposed to be a huge stamp that says non-portable here. So different stdlibs can return different results. Not only that, different versions of the same stdlib can return the same results. Who here uses Visual Studio? Okay, who here uses Visual Studio 2.19? Who here has used 2.19 in the past? Okay, I see hands. So all of you, like the result of the code that has been on the screen has changed between 2.19 and 2022. Because the implementation has changed, and this is fine. So, yeah, I think the real failing, random, is that it serves nobody. Because some people want it to be simple. Some people just want to write, give me an integer. I don't care about where do you get the randomness, the engine, just give me integer in range. Other people want powerful primitives. Other people want to be able to change their random number engines. They want to be able to use specialized distributions and change how they work. And of course, you know, a lot of people want reproducibility. If you have ever played some game like Factorio, which is popular with programmers, that uses, that generates the world from a seed, then you want reproducibility. Because if you don't have reproducibility, then the idea of, oh, I'm going to take a seed and generate world from that doesn't work. And of course, most people also want correctness. You know, and the issue is that random doesn't give you any of this. Now, what will we talk about in the rest of the talk? So we will take very, very high-level view of random. I won't go into details. If you want, because you know how to use it. A lot of posts have been written about that. If you want a reference, we all know CPP reference, and again, go look it up. If you look at the issues of using random, not just the one simple one that I have shown you, but you know, many more that we will run into. And then some basic idea on how can we fix this mess. So what's in random? There is a lot of uniform bit generators or random engines. The standard uses this wording to distinguish between the idea that you generate randomness bits and generating the actual numbers. Correctly, the random numbers that you get from distributions should be called variates. I won't be using that word. You will get statistical distributions. This is how you generate uniform integers, floats, normally distributed floats, whatever you want. And then there are some helpers. It's the catch-all of stuff that doesn't fit into these two categories. And of course, basically all of these are broken. You know, nothing can work properly. So let's talk about the engines. So the random gives you a lot of predefined engines. It will give you a min std-rand 0, min std-rand, merge and twister, another merge and twister, runlux, and a bunch of generators. And you know, you can use any of them. These are the one thing that mostly works in random. And I say mostly because we will get to the issues later. Then you get some adapters. This is the ability to say, okay, I want this random number engine, but skip every other output that I would get. Or create 10 outputs and then shuffle between them randomly. And then there are some generic engine templates. You know, when you feel like you want to define your own Mersenne twister, you can do it easily. It's a very useful ability to have. Now, let's talk distributions. You actually get many distributions in standard. This is actually awesome. Like, you get some very obscure ones. They are split roughly into 5 families. The uniform distributions, that's what you would expect. You generate any number in range at random, equal chance. You get Bernoulli distributions, Poisson distributions, normal distributions, sampling distributions. That's when you say, okay, I have these 5 discrete elements, and I want these probabilities to pick one of them. And each of these hides multiple actual distributions, each of these family. We will not dwell on these, okay? Now, the interesting part of them is that distributions are objects. You know, it's not a function, it's an object. It can be stateful. And the standard doesn't, notice this little note, it's not completely true, specify the implementation, only the statistical properties of the output when you call distribution with unbiased engine. Finally, the helpers. So first one, generate canonical. It will give you single floating point number in range 0, 1, half open. By the way, the fact that it's half open is mathematically important. Okay? And there is a random device. It should give you some random bits to use. And you have seed sequence. This is what basically allows you to carry larger seeding sequence between some source of entropy inside the engine. Okay, that's all of the overview. So what's wrong with random? Well, let's start with the random number engines again. These are the 7 engines that you get. The numbers in parentheses is when they were, let's say, described or standardized. Okay, this one is kind of fuzzy. It should be older, but in '93 it was accepted as the new minimal standard. Like, your random number engine should be at least this good, or it's complete shit. In '93, then these were actually like standardized in 2000s, 94, 81. Notice that like all of them are more than 20 years old. You know, they are all old and they are all slow, at least compared to what we have today. And of course, you know, the good one, the Mersenne twister, which is the good one, is huge. That's 5K. That's 5K. And they are impossible to seed. You can't take a random number engine and just seed it. It's not like easy. I mean, it is easy. You can do this. That's actually pretty nice. So what's the problem? Well, the Mersenne twister, this variant, has 624 integers as the internal state. You give it one unsigned int. It might not even be 32 bits, you know, but let's say it's 32 bits. That's 0.16% of possible seeds that you can give it. Like this, you will fit into one of 0.16% of the initial states of the Mersenne twister that you can get. This does have effects. It means that if you just do this, then there are numbers that the Mersenne twister will never give you as the first output, which shouldn't be possible. For this, it's, I think, either 7 or 13, because one is for naked seeding like this, and the other is for laundering single seed through seed sequence. Anyway, let's use seed sequence. After all, that's what I said is the answer to give more seed state to the engine. So this gets complex, but again, C++ programmers, we can handle this. Okay, so we say, okay, we want 624 elements of unsigned ints, and we will generate from random device all of these elements. We will put them into a seed sequence, and then we will put them into a Mersenne twister. That's reasonable enough, but it's still broken. So I have a question. Where did we get seed data size? We just know, you know, okay, so let's go harder. So how do we get it? Well, std, mt, blah, 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 state size. This is actually very reasonable. So what will go wrong? Let's try it again. Let's try it with the other Mersenne twister. You will say, okay, so we have the Mersenne twister at 64-bit internally, state size, and then we go on. It will compile, and it's wrong. Why is it wrong? Well, this variant of Mersenne twister uses 64-bit types for the internal state, but we are seeding 32-bit types for us. You know, so we already cut the state into half just by doing this. Let's try again. So let's get more complex. Okay, so we have to find out the word size of the state type that we are using. Okay, so it's in bits, so we divide it by char bits. It's the number of bytes in the internal state element. So we divide it by what we get from random device. Okay, so we find out that we have to seed it twice. Then we get the state size again and the data, and we generate the random bits. And okay, you know, like this is how I feel when I explain this. And the issue is, it makes sense. You know, like I think it could be, I wouldn't have to try hard to convince you that what I've shown you is correct, right? It's wrong. It's still wrong. The very complex example is still wrong, and I will show you why in a bit. So let's try generic seeding. Let's try, okay, I have some RNG and I want to seed it. So what do I do? Where do I get word size? Where do I get state size? I don't. Mersenne twister is the single engine that actually has these members. You know, like this wasn't designed to make it seedable. It was just like an accident of standardization that we have these for Mersenne twister, and we don't have these for anything else. Okay, let's show distributions. So another quote by another very smart guy. Who knows him? You know, Nat. So random numbers should not be generated with a method chosen at random. And we have distributions in the standard, and they are irreproducible. You know, we don't have specified implementation. We don't have even specified like behavior past making statistical sense in the long run. So we can't rely on them being the same. And it's actually very trivial to find cases where they are different across different platforms and stdlibs and stdlib versions. They are also opaque. You know, we don't know what's going on. And they are buggy, because of course they are. Why wouldn't they be? So, like, you may think, but why does it matter? It has implications. Why does it matter what algorithm the stdlib uses to implement the distribution? So, example, if you want normal numbers, then you can use box-Muller transform. This is probably the first algorithm that you will find when you search for generate normal numbers. And it only generates values or variates 6.66 std defs from mean. Does it matter? I don't know. It might. You know, 6.66 sigma is extremely unlikely. You have chance 2.7 times 10 to the power of minus 11. This is ridiculously tiny. You know, that's so unlikely that if I had my notebook generating these numbers, then in this talk I should generate about a dozen of them. It's not that unlikely, actually, when you generate a lot of numbers. You know, it's unlikely when you think about it. This is something that can happen to a person once per their life. Unlikely, not going to happen. Generating numbers for simulation in your computer, it should happen all the time, because you generate a couple of them every few minutes on, you know, single notebook that's not particularly powerful. So it matters, but, you know, it might not. Depends on what you do. And let's talk about the bugs, because everyone loves bugs, no? Who here doesn't like bugs in their code? So std uniform real distribution, AB, is specified to return values in AB. Again, half open interval. Again, this is mathematically important, you know? And let's make an example code. This should always pass. You know, by definition, A to B 0 to 1, but excluding 1, we assert that the result is less than 1. By definition, this should always pass. It won't. In fact, it will fail on 2 of the major platforms. libstdc++ is the one that gets this right. libc++ and MSVC will return 1, and you can go to hell. It will fail. Boost, it depends on the version you use. The newest Boost actually does work properly. Older Boost doesn't. That makes sense. So why is this happening? Well, I did say that mostly the distributions are unspecified. This is the one that is actually kind of specified. It's not said explicitly, but there is a strong understanding that if you want to generate uniformly distributed real numbers, you take generate canonical, and then you scale the result. And this is why it doesn't work. Because, oh, sorry. Yeah. I will get to why it doesn't work later. Sorry. Yeah. Now, again, is this problem to us? Maybe, maybe not. We can rejection sample this bug away. We can say, okay, we actually do get the highest result, generate new number, but we shouldn't have to. The other issue is that it's not actually uniform. Uniform real distribution, it should give me uniform results. Does it? No, it doesn't. Why? Because the standard assumes that if I do this, I take A plus X times the difference between them. So basically, I move the starting point and then I scale the second part. Then it will give me the number in AB, assuming my X was in half open interval 0 to 1. This is perfectly true. I can't convince you that this isn't mathematically correct. There is no way I should be able to convince you that this is mathematically incorrect. For floats, floats aren't real numbers. Floats are quantized real numbers. So when you start rounding, it will make some of the floats overrepresented. If you want simple to imagine example, let's say that you have generate canonical that can return all the floats from 0 to 1 non-inclusive. Okay. Now imagine that I say, okay, give me a uniform real number on range 0 to 1 before 1. So I cut off 1 of the floats from the range. Now the scaling has 1 less float to fit. The target range has 1 less float than the original range. So by Pigeonhole principle, 1 of the floats has to be represented doubly. And now it's non-uniform, the distribution. You actually get real issues in less contrived examples, but this is obvious. This should be very obvious why it can't be actually uniform. Okay, let's continue. There are some more specification bugs. I'm going to be honest, these just happen, and it's not limited to distributions or a random. If you ever look through the library issues in C++, you will find that there are thousands of them, and they only 20 or 30 of them are from random. This happens, but they are there. We will not go into them. It would be nice to fix them, but this just happen. You can usually expect your standard library to do the right thing. Let's talk about the helpers. So let's say we generate canonical. It's supposed to generate numbers in 0 to 1, and the standard specified algorithm you can use. It very exactly says this is how you generate the numbers given a source of random bits. The algorithm is, of course, mathematically correct. It's perfectly obviously correct. So, only when it applies to real numbers and not for floats. So again, this will give you 1 if you feed it the properly primed RNG. Say 1 that just returns all bits set to 1, because that's the easiest way to do this. Now, there was another library issue, And it was fixed for C++ 23, kinda, sorta. libcxx and MSSTL will still return 1. If you feel like contributing, you can probably fix it. I'm going to be honest, I don't feel like contributing. It's annoying. So technically it's fixed, but we will get into why we might not want this fixed later. So let's talk about random device. So the first issue, it's allowed to be deterministic. You know, your source of random bits is allowed to be just whatever. What the hell? And the only way to find out is to check the source code of your standard library. You know, you can't check programmatically. In theory, there is a real random device entropy member function. And it should tell you how much entropy there is in the random device. Okay, so the issue is that boost that gives you 32 random bits returns 10. Why? Why not? libc++ returns 0. Why? Why not? Because it can. Like, there isn't anything specified on what it should return, so it, you know, the implementers do whatever. And libstdc++ is very interesting because it either returns 0, or if it's used on Linux, on modern Linux that has like I think it's get entropy syscall, it will ask the kernel how much entropy is there in def random and tell you that. Of course, the issue with like this whole idea, apart from the fact that I don't believe in the def random entropy being depletable, is that, okay, so you ask how much entropy is there, then someone else comes in, gets the bits, and then you get the bits and you came too late. Like, no, this doesn't work. This is time of check, time of use issue. No. Okay, yeah, this is a real issue. So who here has used mingw on Windows to compile code? I see one person. Yeah, so they use MT11937 as random device. It's statically seeded. This was happening until mingw 9 something, which fixed this because they finally realized that, hey, Windows does have some kernel call we could use for random bits, you know. Anyway, ABI compatibility. Who here loves ABI compatibility? Me, everyone. Yeah, so libstdc++ is stuck with this. So now their random device has 5K forever and ever. No, like seriously, there is a union of actual random device implementation and the Merson twister. And this can never change as long as they want to maintain ABI compatibility.
Is it fixed though?
What do you mean fixed?
Does it use the random device or random bits from Windows syscall? Just the structure size?
Yes, the structure size. And this is also on Linux, you know, like this structure size is also on Linux, thanks to ABI compatibility. So yes, if you never used Windows, if you only ever used Linux with libstdc++, this is true because at some point they decided to support Windows with Merson twister as the source of random bits. Statically seeded random bits.
Does it have the same size on different platforms? Because you cannot, the code cannot be linked together. So why?
It was simpler to maintain. Let's talk about seed sequence. Yeah, so seed sequence is completely useless. It has one very simple issue, you know. The standard says exactly which algorithm it uses to take the bits you give it and put them to the output. The algorithm as written loses entropy. So you give it 64 bits of entropy and you get back less than 64 bits of entropy. This is absolutely amazing. And you can actually test it yourself. You can initialize two seed sequences with different bits. You know, there is no magical relation between these bits. And then you ask them to generate two units of output, you know, so this should just be perfectly scribbled from here to here and from here to here. And these two outputs are actually the same. So they lose entropy because you just got different, like the same outputs for different inputs, which means that there are outputs which can't be achieved. And by pigeonhole principle, again, this is broken. Oh yeah, there is more actually. You know how I told you that this complex example of how to seed Mersenne twister is broken? So when seed sequence writes out the output, it does it modulo 2 to the power of 32, 4 bytes every time. Does your engine have more than 32 bits internally? Well, screw you. That's not supported. You know, like, remember this? No, this is all bullshit. You can't ever actually seed the 64-bit Mersenne twister in a way that makes sense. Let's talk about better random instead. So my thesis is that the core design is good. You know, the idea to say, okay, so we have these generators that can give us random bits, and we have these distributions that turn the random bits into numbers. This is good. This is the same idea as we split containers and algorithms, because you have a communication protocol between them that's the iterators or ranges. This core idea is good. Yeah, then we have the implementation. So what can we do about it? Let's start with the engines once again. And fixing the engines requires one simple thing. We say there is now a member that's state size in bytes or bits or whatever, but you know, we have to be able to get the state size. And that's fixed, the engines. Okay, and you know, we want to add some state-of-the-art PRNGs, so we aren't stuck with ones that are 20 years old. More at this point, actually. But this is easy. What can we do about distributions? Well, there are 3 things to fix. So the pointless UB at the start, like just, oh, this is undefined behavior, screw you. This is easy to fix. We just literally delete the clause because there is no reason to forbid the smaller types. Okay, that's easy. Let's go next. Reproducibility. And finally, what can we do about uniform real distribution? You know, because it's wrong, and how do we actually get uniform output? So let's start with reproducibility. And sorry. So one approach, I actually used to advocate this approach back in 2019, is that we keep the names. You know, we still say, okay, it's uniform int distribution, uniform real distributions. And we say in the standard what the implementation is. There is one best implementation. We will get the same result on each platform because the implementation is the same. And that's it. That was 2019. The issue is that it's not extensible. If you do this, and then some annoying smart person named, I don't know, Lemire, comes up with a better algorithm to generate uniform integers, then you are stuck forever because you want reproducibility, and you want good algorithm, and you have to pick one. By the way, show of hand, like, you know, it sounds like who will come up with a better way of generating uniform integers? So who here thinks that it has been less than 5 years since the last time someone came up with new algorithm for generating uniform int distribution, you know, uniformly distributed ints? Less than 5 years. Okay, nobody? One person? Less than 10 years. One? Okay, more than 10 years. Everyone else. Okay, so it's 7 years actually. No, sorry, 2018. That's 6 years. You know, 6 years ago, annoying list are people, person specific, came up with the idea of how to generate uniformly distributed integers, but quickly. More than 4 times as fast as before. So this is a thing that can happen. You know, maybe like in a year, another annoying smart person will come here and say, okay, actually, guys, you are doing it wrong. I have even better idea. So my actual preferred approach, like nowadays, is to just double down on being expert friendly. You know, random will never be really noise friendly, so we just double down. We say this is really for experts or for people who are willing to read a book. And so we standardize the algorithms under their own name. We just say, okay, here you have box Muller transform, you have Marsaglia's polar method, so on and so forth, and we end up with a lot of them, you know, at least 20, and probably more like 50, 60 to be useful. You know, and yeah, there are a lot of ways we could make this more user-friendly. there are tricks to play to have like to make it obvious that like both Box-Muller transform and Marshall Explorer methods generate normally distributed floats and blah blah blah. But fundamentally, the only way to make this scalable is to just standardize the algorithms under their own names. And this does give the fully control to the user. Do they have issue with being limited to 6.66 sigma? Then don't use this algorithm. Use different one. Do they want something that's fast? Use this algorithm. Do they want something that's numerically stable? Then use different algorithm. Now, yeah, I remember that these two are trade-off between numerical stability and speed. Just don't quote me on which one is which, I don't actually remember. One of them uses more transcendental functions when calculating the output, so it will introduce more numerical errors. And let's talk about uniform real distribution and how do we fix it. It's actually very easy and very hard, because first we have to answer a question. What do we mean by generating uniformly distributed floating point numbers in some range, but in general? So we can mean that we want to generate uniformly distributed real numbers in the range and then convert them to floats that are closest to them. This is perfectly valid meaning. In fact, I like it a lot. Or we can mean that we want to take floats in this range and generate it like having uniform chance of picking any of them. Or we can say that we want to generate floats that are uniformly distributed in this range. These are all different things, and very importantly, all of them, every one of these interpretations is useful to someone. The first one is, it can generate any float inside the range. This is interesting for long-running simulations and tests. Two, this is actually perfect for testing. Do you have some, have you implemented something like sinus, cosinus function? Then this is what you want, because instead of having distributed the real numbers, you distribute the float, so you have equal chance of picking any float at random. And this is the one that's actually kind of like implementable, unlike the number one, and it has the same statistical properties over the long run, except that you will never be able to distribute every single number, every single float in the range. You will pick just equidistributable floats in the range and pick one of them at random. Yeah, so there will be a lot of numbers that you will never ever get in the range. That is actually like, implementable. And the issue with uniform real distribution is none of these. None of these interpretation is what you get. And thanks to the idea that we can just standardize algorithms under their own names, we can have all of them. You can just pick the one that you want to use. Well, if someone can tell me what is an algorithm that implements number one, I actually don't know a generic algorithm for this. I know one that does it for 0 to 1. Anyway, let's finish this. So what can we do about the helpers? So generate canonical has fixed the wording. Good. Now, in a few years, all the standard libraries will be fixed as well. But I don't like it, because it fixes option 3. So, it will, yeah. There is 1 billion of representable floats in 0 to 1. It's quite a lot. And generate canonical can generate 17 million different floats. That's 1.7% of the range that it claims to cover. Now, if we do this with doubles, it's 0.2%. It's not even like on the scale. So I don't like this, actually. Does it matter to you? Maybe doesn't. I don't know what your use case is. I know some people who actually care about this. Because if you are using the floats to, for example, seed your simulation, then the fact that there are equidistributed states that you will never start from might matter, or it might not. Depends on what you do. Yeah, depends on the use case. And as I said, I actually do know algorithms that can give you any float or any double in the range. They are possible. They are not particularly obscure. They are quite a lot more expensive computationally than what we have right now. That's the reason why we use what we use. So seed sequence. How do we fix seed sequence? We toss it away. Like there is no like, let's change this one small thing and it will be fine. No, seed sequence is garbage. It needs to be thrown away. What we do then is that we say, okay, it can't ever reduce entropy. If we give it 64 bits of entropy, it has to give us 64 bits of entropy. Like I don't want to find out that I feed it enough bits and it just does something and I don't have that many bits anymore. And it should support any integer type of state. I don't want to have my little engine that uses 64-bit types internally and find out that I can't see that because, whatever, you want more than 32 bits. Why would you want that? And that's for the type. And then when we are talking about the concept in the standard, then we want to use the useful subset. So we can just say, this is a random device. I don't care about the exact data you take. Just seed yourself randomly, and I don't care anymore. Work without me. So that's for seed sequence, and let's talk about random device. At no point should ever a random device be deterministic. Like, I don't care what platform are you using. If you can give me random bits, just don't give me random device. C++ has feature macros. We know how to check, like, is this available on this platform? Just say, it's not available. I don't have random bits to give you. I don't want to find out that it's statically seeded Merce and Twister, and the random device now uses 5K of stack. It's not good use of my stack, of my time, or of the code. Yeah, entropy, I mentioned it. It failed. It was never going to work. Let's drop it. And that's all of the parts that I have mentioned. Is it actually everything that we need to fix? Look, no, it's not everything, but it's enough to make the header useful. If we go through and fix all this, then it's actually usable. Could we do better? Yes, of course. So for example, everything in random can be const.expr. The one exception is random device, obviously. We don't have truly random bits at compile time. Everything else can be const.expr. So it would be nice if it was, but if it isn't, I can live with this. I don't really need it that much. All the generators and distributions should be able to have, I should be able to tell them, okay, generate 1000 outputs to this array, because it actually improves performance quite a lot. Then you're able to just do this. Again, is it important? Like, is it needed to make it usable? No. Would it be nice? Yes, very nice. And of course, yeah, and we want the engines to be seedable with random device. I want just to give it a random device and have them seed themselves without me having to think about how big is the state, and I need a seed sequence, and I need to materialize the data into the seed sequence first, and so on. But yeah, one more thing about the bulk generation. So fun fact, if you want to generate random bits for a random device, you are forced to use 32-bit output. The random device, for example, on Windows, will generate 256 bits, toss away all of them except the 32 that it gives you, and that's your return value. So do you need like 1 kilobyte of random bits? Well, have fun generating 8 times as many in successive calls. Like, no, it's terrible. What else can we do? Yeah, we can clean up various types in the standard to make sense. Like, there is the linear the LCG generic template type class. It says, okay, but you can give me 2-byte integer as the first argument, as what it computes the values in. And then it says, oh, but actually, it needs to be multipliable by some constant that fits into 4 bytes. So it can never be instantiated in 2 bytes because it doesn't make sense. There's lots of things we could clean up because it just doesn't make sense. But I don't think that it would be just nice. Fix the wording. And that's, yeah, a lot of other things, but they're all small. You know, like this is just nice to have. The things before, they're important. Yeah, and that's the end for today. It's time for questions if you have any. And just for the fun, like further reading, you know, like some standardization papers, a lot of my blog posts about random numbers, about the issues with random, and actually about generating random integers, and so on and so forth.
Do you have any suggestions what to use instead?
Sorry.
Do you have any suggestions what to use instead of random?
Okay, so what to use instead of std random? Okay, so it depends on what do you need. So if you need just reproducibility, use boost random. It's reproducible by the simple virtue of being like single code based that you compile on different targets. You know, like boost random doesn't promise that it is reproducible, but it is because it's the same code. But if you want like something more modern, I know that for a few years, the PCG random library was maintained and had a lot of nice utilities. It actually built a lot of utilities over just plain random. Like you could ask it to pick an element in a range, like nicely, without going through generating your own without going through creating your own distribution and so on. Just say, okay, pick one of range and so on. And that's actually the two that I know of for like bigger libraries. If you just want to generate, if you want like better generator, then PCG or s.r.o are good ones, but then you have to get distributions from somewhere. Yeah.
If you go back to the slide with the generate canonical, where you say that
is it in the issues or is it in the?
It is towards the end of the talk, where you say something about the range.
Generate canonical?
Yes.
Do you mean this?
Yes. I'm not sure why the ratio goes down, or what do you mean by different flows? You mean representable or IEEE 754 flows, or?
Yes, this assumes IEEE 754 floats. And so if you say, okay, I want to count how many floats are there in this range in 32-bit IEEE float, then you get 1 point something billion. If you look at how many generators can generate, it's roughly 17 million. It's actually a bit under this. And the difference comes from the fact of how it generates the float, because what generate canonical does is that it basically counts how many bits you need for the mantissa and generates basically that many bits in float and divides it by not divide, it multiplies it by 1/2 to the power of that many bits. It's hard to explain without like drawing it a bit. And this is actually like, this generates a lot less potential floats than there is in the range. And the reason why the difference gets bigger is that basically, okay, how well can you imagine when you look at like the bit representation of a float, what it looks like when it's set to 1?
Okay, you mean that not all bits are used to represent the final, or let's say there are not a number space and things like that.
No. Okay, so when you have float that's set to 1, the first bit set will be the third one. You have the sign bit, you have the highest exponent bit, and then you have another exponent bit, and that one will be set. And then basically you have few set, then you don't, and then you don't. Most of the months I have set for this to work, right? And that gives you for double, very roughly, like the rough estimate, 2 to the power of 62 potential floats in 0 to 1. It's something like 61.997 or something, you know, like very roughly 2 to the power of 62. Then you have 53, I think, bits in the mantissa. And that's how many different doubles you can generate by generate canonical. If you generate more, you actually start having issues with non-uniformity due to rounding in the final division. Because what you do is that you generate a number that's between 0 and 2 to the power of 53 exclusive and non-including, and then you divide it by 2 to the power of 53. And because you have 53 bits in mantissa, this just works out to being uniform without issues with rounding. But it does mean that it's like a lot less than the 2 to the power of 62 that there are actually potential floats in this range.
And why do you think there are so many issues with the implementation? Like, what is the reason that there are so many small or sometimes
it depends. Okay, I'm going to give one example, like of what I think is just yeah. So this issue, right? Oh, I'm going to go back without the meme face. So why is this a thing? Okay, so what is true is when you are down to single byte integer types, then for some of the distributions, you can start running into precision issues, right? And what I think has happened here is that, okay, like 1 byte is too short, we will forbid it. And because this is like very early in C++ 11, very early in the standard, then they use the it's undefined wording, because back then we didn't have the experience with saying basically static assert and don't like, you know, we didn't have the experience of how to word this you shouldn't do this, but the implementation is expected to catch it for you. It's not just UB. Then you have other things which are like the generate canonical old wording. So distributions, issues, random numbers. No. Yeah, this one. You know, like, yeah, this just comes, like, this on the other hand comes from, I guess, inexperience with floats. Because, you know, like, the algorithm is correct unless you realize that you are not dealing with real numbers and that the rounding will get you.
So why don't we just tell this in this style of like decimal numbers? We get like if this was in decimals, it would be like the equivalent of getting a random number between 0 and 1.
Mm-hmm.
And you have 4 decimal numbers. It means that, well, in the decimal, in that case, it means there's always 4 numbers after the 0. It means you have 10,000 possibilities. And if we translate it, and we are able to write numbers that has like 5, like we write it with 5 digits.
Mm-hmm.
And yeah, we can use an exponent. So in practice, we can write a lot of numbers with this style, but we can choose only a small section of them, and that is those that are represented by 0 and 4 digits afterwards.
I actually don't understand the question. Sorry.
I mean, this is how, because we can just tell this into decimals, and this is like quite well. So
okay. I'm going to open text editor and Where is it? Okay, it's here. I guess the question is that if you have floats that are defined kind of like this, you have, I don't know, like 0.1 to, no, you have to start with number. So if you have like decimal floats and then you operate on top of them, is that the question?
No, it's just a question more like the time think about the answer.
Yeah, I think that's actually like, so I get to use like example of this, like of decimal floats on my last talk. And when you think about it, you have like these you have like lot of small numbers, you have say, right? Sure. Like this is close to the smallest number if you don't do the normals and so on, right? And the issue, yes, the issue comes from the fact that instead of saying, okay, so I can just generate the last 3 digits, then you have to try to catch like these small numbers as well. Except then these like last digits don't make sense for help me out here. Yeah, these last 3 digits don't make sense for bigger numbers, for like, I don't know, something reasonable like 1.22, I said the of -1. Like they don't make sense. And what we could do to catch all of them is to always generate all 9 digits. You know, have like the full expansion and then pick float that's closest to them. Right? That's the algorithm that gives us all possible that's the decimal floats in this range. But it actually is. It actually would be. Like if you say I've generated random numbers, we will always assume 0, and I generated blah 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 blah. Then I can find the closest decimal float to this, and it will be perfectly uniform always, assuming I generate digits uniformly. The issue is, it is true.
But when you truncate it, then you have like bajillion numbers mapped to just one number.
That's not a problem as long as yeah, that is not a problem.
But it's not uniform.
It is uniform because
But I just say that when you generate like a million numbers, they all map to one truncated number.
it's not a problem as long as okay, so what we will get is some, okay, let's assume that we have shorter float because I don't want to write so many digits. Okay, so let's say that we have just these 2 digits that are relevant to us. So yes, this and let's change to 4, this one to 5, this one to 6. Like, yes, these all will round to 0.24. The reason it's not an issue is that we have the equal in uncountable infinity that counts that will look like this. 2, 4, let's make this a 5. That will round down to 5, and we will have similar to round up and so on. Every decimal float like this will have a probability of being picked that's equal to the range of real numbers that they represent. Even though they are, you know, it's all uncountable infinite and blah, blah, blah. This actually does work. The issue isn't that you map multiple numbers to one. The issue is when the sizes of the mapped sets are not equal. And even when they are not equal, it's okay, as long as the size of the mapped sets corresponds between floats that all encompass the same range, length, on the decimal line.
Yeah, but that's not true either, because when you truncate it, you have the
Yeah.
this up, but you have different exponents.
What do you mean?
Yeah, when you truncate it to the probe precision,
Yeah.
connected to decimal numbers, then no.
So the trick is that yes, the smaller numbers will cover a smaller part of this, but when you sum up like how much they cover in the line length on the decimal line, they will have the same chance of being picked. This actually works, and this is like something similar to this, except you do it with binary extension, is how you generate every possible float in 0 to 1. The issue, generic canonical, it does something different. Because it's much faster, you know, like if you want to do this for double, and you have 64-bit random number engine, you can find yourself calling this random number engine up to many times, give or take a bit. If you do the generic canonical way, where you generate number between 0 and 2 to the power of 53, and then divide it by 2 to the power of 53, then that's single call to the random number engine and single division. Okay, more questions?
Yeah. Question, can this be done simply by choosing a random integer and simply filling the matrix up?
No.
Using something arithmetic and then you just
So,
the results to...
Yes, this is a common trick. It has one issue: your lowest bit will always be 0. Because by subtracting, so you will generate 1 between 1 and 2, and you just fill in the mantissa. That's actually like a cool trick. Then you subtract 1, and hypothetically, you will go down to 0 up to 1. But the issue is that between the rounding and so on, you don't have the lowest bit of the mantissa.
I can just reuse one more bit from the long integer I have generated.
Yes, and I will actually have to think about whether this is then uniform or not.
Well, actually, yes, this would be a problem because yeah.
So, but actually, like, so, like fun fact. So, how do you generate actually uniform floating point number? You know, I have range A to B, and I want to generate actually uniform floating point number in this range. So the first part is accept that you can't do this. The second step, so you will decide whether you care more about having the last number past the range or before the range. Because not every range of floats can be divided into equidistant floats. And if you can divide it into equidistant floats, then you can generate uniformly distributed floats. Okay? So you will have to decide whether like you want to cut off part of the range or whether you are okay with the last float being like closer than it's supposed to be. You pick one. Then you count how many equidistant floats are there in this range. And you generate random integer which tells you which one to pick. That's literally the whole trick to generating uniform reals in range. The issue, of course, is that this leaves you with lots and lots and lots of floating point numbers that you can't ever generate in any range. That's not any worse than you had before.
We don't need like all of them. We just assume something with 4 decimal digits to be random, and otherwise just to be well distributed. So we may just, in that case, reuse this trick with just setting the mantissa from integer and offsetting. We use some precision, but we might not care about last bit.
Yeah. Okay, more questions?
Well, did you look at the possibilities? How can you actually reuse some of the split random and not the rest? For example, you define your own Merson twister so that you are sure that this is the one that all of my code will use. And then you just use it with the rest of the library.
So yeah, the engines are actually like the least issue. And it depends, like if you don't mind, you get different results on different platforms, you can use distributions. If you don't mind that your random number engine is slow, you can use engines and so on. So the question is like, which of the issues that they have, you can tolerate. And you can just say, okay, I can tolerate lacking reproducibility, I can tolerate that it's slow. And then you just check that the platforms you use have like sane random device, and you are fine. Or you can say, oh, I actually can't deal with non-reproducible distributions because I need them to the same results across different platforms. In which case you can include boost random or write your own if you have a simple one, and you can use the engines and so on. But like all of the parts are flawed in some manner, so you have to pick which of the flaws you don't mind. There aren't any parts that are perfectly fine.
It's actually a random device that gives you a random number. What is it doing internally actually?
It uses a system call to do it. It can't do it on its own as like defined in the system. It has to understand what platform it targets and say, give me randomness. So for example, libstdc++ opens either random or urandom device and reads from there. The MSSTL read calls some system call that's like secure random and gives a bunch of random bits back.
And how do you know whether it does this random or random?
Sorry, how do I know?
And like on Linux, does it keep random or do random? Because like
you can pick. By default, it does something. Again, implementation defined. And so random device has string constructor, and there are no defined arguments that do anything. But on libc++ and libstdc++, you can tell it which of these devices to open. In fact, libstdc++ actually allows you to open an arbitrary file through the arguments to random device and read that as your random bits, as long as it's fine. Yeah, you can just say, okay, open my file, and this is good.
okay, so as long as it's right result into a file and get it to open that file.
Yeah, like if you do this with libstdc++, that's fine. Then it will just read back to your file. libc++ actually doesn't let you pick. Will tell you to get lost if you give it argument it doesn't know, which is I think def random and def urandom only. Okay, I think that's all of the questions. I think it's time to get a beer.